You know, we tend to think of a diode as one of the simplest things in electronics, right? It's just a one-way street for current. But what if I told you that this humble little gatekeeper has a secret identity? Understanding it is absolutely crucial to how our modern, high-speed world actually works. So, let's dive in.
We're going to peel back the layers of the common PN junction diode and find a dual personality that's been hiding in plain sight this whole time. Turns out, that simple one-way street for electricity, yeah, it's also a secret storage device.
So here's the big question, the central puzzle. On one hand, you've got the diode. It lets current flow one way, blocks it the other. Simple. On the other hand, you have a capacitor, a thing designed specifically to store electric charge. I mean, what on earth could these two possibly have in common?
And here it is, the big reveal. They both store charge. Under the right conditions, a diode doesn't just direct traffic, it holds on to charge, acting exactly like a capacitor. And this isn't just some minor little quirk. It's a fundamental property that engineers either use to create amazing things or have to fight against in high-speed circuits.
Okay, to really wrap our heads around this, we need to do a super quick refresher. Let's look at the basic blueprint of a capacitor. What really makes a capacitor tick?
It's actually beautifully simple. You just need two things that can conduct electricity. We call them plates. And you stick something in between them that doesn't conduct electricity. That's our insulator, or dielectric. That's it. That's the core recipe. And this picture shows that recipe perfectly. You see the two conductive plates on either side building up their charge, but the real magic is that insulator in the middle. It acts like a barrier, stopping the charge from just jumping across. It forces it to be stored. So just remember that three-part structure: conductor, insulator, conductor. Got it? Good.
All right, time to pivot back to the diode. The real action happens right at its core, at a place called the PN junction. This is just the spot where two specially prepared pieces of semiconductor material, a P-type and an N-type, come together.
So you might be asking, wait, how do you get an insulator inside a semiconductor? Well, it happens naturally. As soon as the P and N materials touch, electrons from the N side rush over to the P side, while these things called holes, think of them as positive charges, move the other way. They meet right in the middle, cancel each other out, and bam! This creates a little zone right at the junction that has no free charges left. It's called the depletion region, and, this is the key part, it acts just like an insulator.
Now, this brings us to the diode's first secret identity, its first capacitive personality. And this one only shows up when the diode is turned off, or as engineers like to say, when it's reverse biased.
See, when we apply a voltage in that off direction, we're basically pulling what's left of the free charges even farther away from the junction. And what does that do? It makes our insulating depletion region even wider. And all of a sudden, that structure should start to look pretty familiar.
And here we go, the analogy laid out crystal clear. Remember our capacitor blueprint? Well, the two conductive plates are just the P-type and N-type regions of the diode. And that crucial insulator in the middle, that's our depletion region. The structure is a perfect match. It's the same thing. This effect has a name, of course. It's called transition capacitance. And here is the really cool part. Because the width of that depletion region changes depending on the voltage you apply, it's like having a capacitor where you can actually change the distance between the plates on the fly. That is an incredibly powerful tool.
But hey, that's only half the story. Let's flip the switch and check out the diode's other secret identity. This one appears when we turn the diode on or forward bias it.
Now, when we let current flow, that insulating depletion region we just talked about, it shrinks down to almost nothing. So you'd think the capacitor effect would just disappear, right? Nope. Instead, a totally different and frankly shockingly larger type of capacitance just appears out of nowhere. We call this one diffusion capacitance. Now, this isn't caused by a static insulator, not at all. This is caused by the massive flood of charge carriers, all those electrons and holes that we're actively shoving across the junction. It creates a temporary pileup, a little traffic jam of charge, as they all wait to cross over and find a partner. So the best way to think about it isn't static plates anymore. It's more like a big crowd trying to get through a single gate. The capacitance here is really just the time it takes for that crowd of charges to build up at the junction, and then the time it takes for them all to clear out once you turn the voltage off. It's a totally dynamic kind of storage.
So just how much larger are we talking about here? Well, to put it in perspective, in the off state, that transition capacitance might be a teeny tiny 1.2 picofarads, but the diffusion capacitance in the on state, that could be over 385 times nanofarads. That's not just a little bigger, it's over 300,000 times larger. It's a completely different beast.
Okay, so a diode has two different capacitive personalities. One is small and controllable, the other is enormous and kind of slow. And trust me, this is not just some neat piece of trivia. This has huge, real-world consequences for literally every electronic device you own. So let's just nail this down one more time. When the diode is off, you get the small transition capacitance because of that insulating layer. When the diode is on, you get that massive diffusion capacitance from the traffic jam of moving charges. Two states, two different causes, and two wildly different sizes.
And this dual nature, this is a classic engineering trade-off. This hidden capacitance can be an incredibly powerful tool on one hand, but a really major problem on the other. It's a double-edged sword.
Let's talk about the good side first, the tool. Engineers took that small controllable transition capacitance, remember the one that changes with voltage, and they built a special kind of diode called a varactor to take advantage of it. It's basically a voltage-controlled capacitor, and it's the component that lets your car radio scan and lock onto different stations.
Now for the problem side. That enormous diffusion capacitance, that traffic jam of stored charge. Well, when you need to switch the diode off, you first have to wait for that entire traffic jam to clear out. This creates a delay, a lag. And for something like your computer's processor, which switches billions of times every single second, that lag is the ultimate speed limit.
So the next time you see a simple diode, remember its secret. It's not just a one-way gate. It's a complex little device with a split personality, one that's responsible for both tuning our radios and for putting the brakes on our digital age. It's just a perfect example of how, in the world of electronics, even the simplest components have these incredible hidden depths that shape the technology we use every single day. Thanks for joining me for this explainer.